when I was asked to come and do this talk, I realized that I was going to be speaking at an institute that services predominantly the rest of Southern Africa, or the rest of Africa. And so I wanted to talk about where we're heading in this golden age, as Jeff put it. And so my talk is it's gonna jump a little bit between some of the science, some of the technology, some of the social aspects, some of the political aspects and decisions and policy decisions that have gone on. Hopefully just to give you an idea of and a sense of warmth and fuzziness about where we're going with opportunities for professionals and technologists and engineers and scientists, mathematicians and so on. So I hope you get that sense from what I want to share. But the point is, when we're talking about radio astronomy, we've got to set a couple of fundamental common talking points. And so I just wanted to put up this image, which is typically the beginning of any public lecture on radio astronomy. And it basically gives us a reference point so we can talk about the same sort of thing. Now, when people typically think about astronomy, they think about telescopes, optical telescopes. They think of sort of looking at the stars on a nice dark evening. And the concept of radio waves don't necessarily come into it. Those of you who have had the fortune or misfortune of doing at least a first-year physics course will at least know that there is fundamentally no difference between the light that we see on a very dark evening when we look at the stars or the kind of signal that we measure with our radio telescopes. They're all part of the electromagnetic spectrum. And so it's just a matter of looking at the universe in a different way. But before we head down this road of looking at the universe through radio eyes, I just want you to spend some time thinking about why it is that most of the organisms on this planet have evolved to have electromagnetic sensors at a specific portion of the electromagnetic band. And what port are we talking about? Well, if you have a look here, we have the electromagnetic spectrum. And somewhere over here, we have the visible light portion of the electromagnetic spectrum. And we all see, our eyes, our antenna in our heads, are sensitive to that portion of the electromagnetic spectrum. Now, I want you just to maybe think about it just for a second. Why? What was the unique set of circumstances that conspired that organisms on this planet, the majority of them, are all sensitive to just that portion of the electromagnetic spectrum? I mean, for example, why do we not see things at X-rays? Or why do we not see things at, I don't know, what is the typical radio station here, 94.5 or something megahertz? Why have these sensors evolved? And it's a bit of a confluence of two things. The first is that the source of most of the electromagnetic energy that we experience on the surface of the Earth is our local star, the sun. And it turns out that the temperature of an object relates to the amount of electromagnetic energy it gives off. And it turns out that the sun, at its surface temperature of about 5,000 Kelvin, has a peak, gives off most of its energy round about the visible portion of the electromagnetic spectrum. What that means, if you pick another star at a slightly different temperature, it is going to have a peak at a slightly different frequency. You can also follow that on and realize, well, actually, it's not just a narrow peak, it's a very smoothly varying peak. And so that means that anything that is at a non-finite temperature gives off electromagnetic energy. You give off electromagnetic energy. Now, in my days of talking with public talks before, I came from a small town called Hermanus, where we have some very free-thinking, open-minded people, and they always wanted to challenge me on this idea of what a person's aura meant and how much energy they gave off. But fundamentally, let's leave that aside and realize that the sun, our star, gives off most of its energy at the visible portion of the spectrum. And that the other thing that this graph shows, and it's not really clear on here, but there are these gray shaded areas here that you can almost think of as clouds. What those gray shaded areas represent is the ability of the atmosphere to prohibit or stop electromagnetic energy coming through. And it turns out that there is a gap in these clouds right about the visible portion of the spectrum. And so you see two things conspired on the surface of the Earth. As organisms evolved and developed the kind of characteristics that they do, they were firstly bathed in a huge amount of electromagnetic energy that happened to be at the visible portion of the spectrum, and they were shielded by the atmosphere from a vast number of other frequencies in the electromagnetic spectrum. But why this is significant to radio astronomy now is we've now built the technology to build eyes that are sensitive to this portion of the electromagnetic spectrum, which means we can build instruments on the surface of the Earth that will be able to receive signals from pretty much anywhere in the universe. It also means that if you want to see the universe at frequencies either below this window or possibly in between there or higher up over there, and we do have instruments that are sensitive to those frequencies, you actually have to put them on a rocket and send them above the atmosphere. And they have to park either in orbit or put them on some other platform. There's even talk of putting radio telescopes on the moon one day, which would be a really nice project to be involved in. But I just wanted to start off with this sort of background, just to sort of let you know what are the kinds of signals that we're receiving. The other very predominant signal that manifests itself in the radio astronomy arena today is an emission from hydrogen. Now, if you took a cloud of hydrogen and put it in a container and pointed a very sensitive radio receiver at that hydrogen, you would measure a very distinct frequency. And that frequency is related to the physical property of hydrogen in that the spin, a nuclear property of the components of an atom, are either up or down. And if these two spin from the nucleus and the electron of a hydrogen atom are aligned, then the atom is at one energy level. It has a certain amount of energy associated with it. If one of those spins is in the opposite direction, then the energy level is different. And the difference in energy level can be related to an emission of electromagnetic energy. And it turns out that that frequency is 1.42 gigahertz, so on and so on, so many significant figures. It's a very exact, well-known frequency, and it's a characteristic of hydrogen. The next thing that we do is we start to think about, well, why is hydrogen significant? And that's because it is the most fundamental atom. And ultimately, all heavier atoms, all more complicated atoms with more components to their nucleus and more electrons and so on, had to have some stage been built out of hydrogen. So the chemical constituents that you're made up of, the molecules and atoms that make up this piece of stick, all at some stage started off as a hydrogen atom. And through the process of nuclear synthesis in stars and supernovas, so those atoms were fused together through nuclear fusion to make more heavier and heavier elements. But because it is the most fundamental of the elements, we find that it is the most commonly found element in the universe. So it means that it doesn't matter pretty much where we look, we're going to see hydrogen. And so if we build a radio receiver to that frequency and we point it, then surely we should be able to see that frequency. The next thing that we do is we make use of a principle that our colleagues in the traffic department use for trapping us, those of us that speed on the highway. And that's a phenomenon known as Doppler shift. And what Doppler shift means is that if you have something that is emitting a radio frequency and it is moving relative to you at a certain velocity, then it'll appear as though its transmitted frequency is different. If it is moving towards you, the frequency appears slightly higher. If it is moving away from you, the frequency appears slightly lower. And this is very useful to us because if a galaxy far, far away has the most common element in it, hydrogen, then we expect if we look at that galaxy, if that galaxy was stationary relative to us, then we would see an emission of that frequency. If the galaxy is moving relative to us, then we will see a Doppler shifted version of that frequency. And it turns out that as we study cosmology, and we'll talk about this a little bit later, that's one of the observational ways we've been able to put sort of current understanding of the universe as 13 to 14 odd billion years old, is our understanding of how the universe must be moving relative to where we are right now, and we measure it by looking at what the Doppler shifted hydrogen frequency is. So those are the two sort of fundamental building blocks that I'm going to build on as I talk through the rest of the radio astronomy emissions that we're going to be measuring. The one is that anything that is at non-zero temperature, which is pretty much everything, is going to be giving off radio waves. And the other thing is that looking at specific either elemental compositions or molecular compositions, we can look for specific radio frequencies and study those radio frequencies to understand a little bit more about the dynamics of the thing we're looking at. But like I said, I wanted to talk about a little bit of policy as well, as this is an African-centered talk. And I wanted to throw up this from it's an excerpt from the Department of Science and Technology's strategic plan for round about this time. It's supposed to be from 2011 to 2016. And most significantly, it is this highlighted section. It is in the country's national interest to facilitate the modernization of African economies and the development of their national science, technology, and innovation capacities. And so that is an official policy of this South African government, is not only to develop South Africans' capacity, but to develop other African countries' capacity as well with respect to science, technology, and innovation. And so that's the platform at which we start. And like I said, this policy drafted maybe prior to 2010, but it's been around for a while, and we'll hopefully look through some of the investments that have happened by this country and the kind of influences and impact that what has happened in this country is doing, hopefully, for the rest of Africa. So let's start with that. The other thing that we're going to look at is why is this significant for Africa? And this is a slide that I've stolen from a colleague of mine who works in the outreach, the astronomy desk for the International Astronomy Union, and he's looking at how astronomy can be used to teach and to improve science education. And we're not going to go into too much detail of what the axes of all of these graphs, but you'll notice that there is a double peak in almost every single one of these graphs. And basically what these graphs show is they show some kind of score on the x-axis, whether it is basic reading literacy, whether it is numerical skills, whether it is the scores at some kind of standardized assessment. So the further you are to the right, the higher the score, the further you are to the left, the lower the score. And then on the y-axis is the amount of people within a certain grouping. And what you always find is that this split, this bimodal split, is typically split on either racial grounds in Southern Africa or economic and social grounds pretty much in the rest of Africa. And what that tells you is that there's two groupings of people who do well, and they typically come from wealthy white backgrounds, and people who don't do well, and they typically come from non-white, poor backgrounds. And this is fact. This is scores, standardized scores that have been assessed. And so this is not a fiction that this is something that we have, we're living in a bubble. We need to take cognizance of this fact and do something about it. And investing in science and technology, innovation and understanding and education will hopefully not bring the one group down, but bring the other group up, so that there is a standardized, doesn't matter what kind of social background you come from, what kind of racial group you come from, you all have the same chance to succeed. And hopefully that's what projects like radio astronomy can do to upskill and give people opportunities. This next graph just talks a little bit about why radio astronomy is such a significant thing in Southern Africa and what it means to build a radio telescope. So the first thing is you'll notice South Africa there. What the colors show you is the colors show you where there are people in South Africa. And there are a hell of a lot of people down here in Cape Town and the peninsula, not so many around there on the other side of the peninsula. It's because the water's too damn cold on that side. But you'll notice that there is a big gap of people in this portion over here. By the way, red is about 250 people per square kilometer, and white is 0 to 4 people per square kilometer. So you can see that in this portion of the country over here, there are hardly any people. In fact, every time I look at this, I almost think that somebody took a line and traced where there are no people in the country and said, right, that is the Northern Cape, and the rest is the rest of South Africa. But this is important because when you build a radio telescope, those radio frequencies that you need to be sensitive for can be interfered with by our common electronic gadgets. our cell phones, our microwaves, even the cars that we drive interfere with the sensitive receivers that we build. And so we want to try and be as far away from those kinds of radio emissions as possible. The next thing is when we build our radio telescope, and these kinds of telescopes you can almost think of as digital cameras. Now, if you go shopping for a digital camera, what are the two things that you're going to be paying for? Think about it. The two things you're paying for when you buy a digital camera. The one is pixels. Right? The more pixels you get, generally the better camera you have. Not always. Because the other thing that is the limiting is the size of the lens. Right? The bigger the lens, again, the better quality pictures you can take. You've only got to think of all the sports photographers that sit next to the side of a sports field. They've got these massive telescopic lenses with a large big aperture and many pixels. And that's what we want to build with our radio telescope. And the way we do that is the more purple dots you see, that's a good analogy to the more pixels we have in our camera. So we want as many of those purple dots as possible. The other thing that we want to do is we want to make the purple dots as far away from each other as possible to get as big a lens as possible. And so this kind of spiral shape that you see is what is needed to make those pixels. And we want them to be far away from people, so that's pretty much there. We want enough space that we can make as many of these purple pixels, and we want them to be as far away from each other as possible. If we have those characteristics in place, then we can build a pretty good digital camera to take radio pictures of the sky, and that's ultimately what we're going to be after in this. And so that allowed the national government to declare this zone over here, which they call the Karoo Astronomy Reserve. And there is an act of parliament called the Geographical Advantage Act, which allows the government to regulate anything that goes on inside this area and regulate whether or not whether or not it can impact our ability to conduct observations, radio observations. And so, like I said, a lot of support from the government to be able to do this. And why do we need this area? And because of this area, we have the what we refer to now as the heyday of radio astronomy. So in South Africa, pretty much radio astronomy observations started in 1975 at what is now the Hartbeespoort Radio Astronomy Observatory. And pretty much it was the only bastion of radio astronomy technology in the whole of Africa up until this notion of the square kilometer array was hatched and where to put this huge, big digital camera. And as soon as the idea was seeded and we got the government on board and they created this geographical area, this Karoo Reserve, then things started happening. We had the Americans come and deploy a telescope called Paper, and I'm going to go through each of these telescopes in a bit more detail, but that was in 2009. So an internationally funded cutting-edge telescope that is here. Shortly after that, the very first SKA precursor built in Africa, the first interferometric array doing science in Africa, CAT7 began its full operations in 2012. This year, hopefully, CBAS, another telescope that is internationally funded and internationally inspired, again deployed inside that Karoo Astronomy Reserve because of the uniqueness of that portion of the country. Meerkat will come online in 2016. We already know that SKA Phase 1 is going to be built in Africa. SKA Phase 1, well, SKA Phase 1 is about 10% of the final SKA. And SKA Phase 1 is 256 dishes in Africa. So you can do the quick sums. That's in excess of 2,000 dishes that will get built for SKA Phase 2 at some stage. Right? We have to build SKA 1, show that it delivers cutting-edge science, show that it can do what it's supposed to do in Africa, and only once that has happened will we start building the rest of SKA. So a bit of history and the different telescopes. So this is Hartbeespoort Radio Astronomy Reserve. It was actually built in 1961 as part of the NASA Deep Space Network. It's the only way that NASA could see its vehicles in space. You needed a distribution of stations around the world, and so they built this one in South Africa. It operated until 1975 when NASA pulled out of South Africa. The site was handed over to the CSIR and it was converted to a radio telescope. And it's been operating as a radio telescope since then. Apart from about a year or so in this period where its main bearing cracked and had to be replaced. But pretty much continuous observations as a single dish, 26-meter diameter radio telescope operating. And this is effectively the cradle of radio astronomy in South Africa, and it's because of the work that was done at this facility that the SKA is definitely coming to South Africa. So like I say, HART still continues. It's a single dish, which means that it doesn't really operate like a digital camera. It just detects whether or not there is emission, but because its dish is so big, it can detect emission from very small patches of the sky. And so it's able to, like an old raster printer that prints backwards and forwards, it's able to build up pictures of what the sky looks like. So it can build up total intensity images of the sky. It can measure spectral emission, so it can determine whether or not there's hydrogen coming from a certain portion of the sky, or whether there are any other spectral emissions coming from other chemical elements or molecules. It's part of the pulsar monitoring network, and so basically what pulsars are, they're the remnants of a supernova. The stuff that gets left behind in that explosion gets compressed down. The mass is typically the mass of the sun, so it's around about the same mass of the sun, and the diameter of one of these neutron stars is about 13 kilometers. So it's quite a dense region of matter, and because of the interaction of the particles, you get these jets of radio energy that come out from the pulsars, and as these pulsars spin, so when the jets of radio energy are directed towards you, so you get a flash of radio energy, and that we call a pulsar. And so HART has been measuring these. Another thing that HART does is that, there it is located there in Africa. It's part of an international network of radio telescopes that we use to measure how the Earth is moving. So the nice thing about the universe is pretty static relative to where we are. And there are certain sources of radio energy whose position in the universe is so well defined with respect to us that subtle motions in the Earth's crust can be detected by looking at the difference in observations from those signals. And it turns out that if you have a look at this, this portion, well, in fact, I guess the whole of Africa is moving in that direction at about 2.5 centimeters a year. So it's not a lot, but it is detectable just by looking at reference signals from certain radio sources. Other places, the length of this line is determined the scale, and that little arrow there is about 10 millimeters per year. So, in the middle of the Pacific, they're heading off at a large rate of knots. And this is important because there are a lot of astronomy observatories located on Hawaii. I can't think of why anyone would want to go and live in Hawaii, but there they go. The other thing that this image shows over here, if you remember, I said there were two things that we chase when we're building radio telescopes. The one is number of pixels, and the other is you want to make the pixels as far apart from each other as possible. So why not take it to extreme? Why not just use pixels only here in South Africa? Or why not use dishes that are only located in Africa? Why don't you link together dishes from all around the world? And that's what they do in a system called very large baseline interferometry. And so basically what you do is you take radio signals from all these different radio telescopes around the world, you timestamp them very accurately where they were recorded, and you bring the data together and then you form the images. But it turns out that just having the dishes far away from each other isn't enough. You actually want to try and have as uniform a spread of where these dishes are located in order to make as accurate images as possible. And so currently, the only place in Africa is Hartebeer's Hoek that links up to this network. And you can see that it ends up linking all of these antennas that are in the US with the European VLBI network in Europe and our colleagues in Australia. And so had HART not been there, there would be a huge gap in our ability to form these images in this network. And it's actually, you'll notice that this absence of telescopes in this portion of Africa has led to the African VLBI network, which is something that I'll talk about a little bit later as well. But again, that's using that principle of trying to make your dishes as far apart from each other to make as accurate images as possible. So we'll start with PAPER. PAPER was that American telescope that was deployed on site. It is, here you can see 128 of their dishes located in the Karoo. PAPER is an acronym for a rather long and confusing sentence: the precision array for probing the epoch of reionization. Right? Precision array, well, that shouldn't take too much to get your head around. You want something that can measure the signals very precisely. What about this epoch of reionization? Let's break it down. Epoch, well, epoch is just a scientific way for saying event or a timestamp or some kind of moment in time. And so basically what this array, this telescope is doing is it's looking for a certain moment in time. And what moment in time is it looking for? It's looking for a period in time when the universe reionized itself. So let me give you a little bit of cosmology, and this is where I must admit I'm going out on a little bit of a limb. I'm sure there are people with a much greater understanding of cosmology in this room than what I have, but I'll do my best, so just bear with me. Current understanding of how the universe evolved is that there was a Big Bang. Something released a large amount of energy, and that energy spread itself out and effectively dissipated itself. And as everything spread out, the temperature went from very hot at the instant of the Big Bang, and as things started spreading out, things started getting colder and colder and colder and colder and colder. And eventually you got to the stage where everything was so spread out and so far apart from each other that everything was effectively sitting at absolute zero. So we were not getting any radio emissions, no signals coming from that emission. And things stayed like that for a portion of time, which we refer to very imaginatively as the Dark Ages. Dark Ages because we weren't getting any radio emission from them. But during this time, all the fundamental forces were in place, and so gravity was acting on all this matter that had been spread out. And so you had little pockets of over-dense areas, and those pockets of over-dense areas started attracting more and more matter together. And of course, as you start bringing things together, bringing matter together, the more stuff you have, the larger the effect of gravity is going to have. And so the nuclear forces started fusing things together. And as they started fusing things together, there was suddenly now a new level of energy, very localized, but there was enough energy to reionize, to ionize the atoms. And it was at that moment that we have this moment of this epoch of reionization. So that's what they're looking for with PAPER. And how do they plan to find it? Well, they're looking for hydrogen. And again, we think back to hydrogen. Hydrogen's got that specific well-known frequency, and that frequency is 1.4 gigahertz. Now we start thinking about our theories of cosmological evolution, and we start thinking, well, if the universe is expanding and accelerating, and it is 13.4 billion years old, or however, then we can measure and we can predict by how much that 1.4 gigahertz signal must have been Doppler shifted. And it turns out that it's Doppler shifted to the order of about 100 to 200 megahertz. And those are the frequencies that this array is looking for. It is looking for signals at a frequency of about 100 to 200 megahertz. And if they find that signal, then again it dovetails in perfectly with our understanding of how the universe has evolved. And so you can take a very, what would otherwise be esoterical theory of how we know what happened 14 billion years ago and use observations today to try and understand and map what was happening there. So it's a very, very clever technology borrowed from our traffic officials. CBAS is a two-dish observation of the all-sky. And basically at C-band, around about 5 gigahertz, and it's a single dish, so basically it's just scanning around, having a look at the sky. And what it wants to do is it wants to build a picture of where there is radio emission and where there is no radio emission. And it's two dishes, one in the northern hemisphere and one in the southern hemisphere. This plot that you see here is the current northern hemisphere data. This gray area is what the southern hemisphere telescope, the one out on our site, will be able to see. And like I said, it should come online a little bit later. Why do we want this? Well, like I've said, anything that is at a finite temperature gives off radio waves, and it'll give off different frequencies. So there already exist observations of the all-sky at other frequencies, for example, this one at 23 gigahertz. And what we want to do is make an observation at 5 gigahertz to see what is the frequency dependence of these emissions. And knowing something about the frequency dependence, again, tells you something about the emission mechanism that created that signal, and also tells you a little bit about the way the signal is propagated through space as they move towards us. Other telescopes that are really doing science, these are observations of a galaxy not too far away, observed by the CAT-7 telescope. And again, we're making use of hydrogen here. The grayscale image over there is what you would see if you took an optical image of that portion of the sky. And so you can see that there's definitely something going on in the middle here. But if you look at it just optically, you would say that the extent of this galaxy is pretty much limited to that dark area over there. When you image it using hydrogen, you see that there is actually a large significant portion of the galaxy that you don't see with optical signals. And again, this is another reason why having radio telescopes is a useful tool, because it allows you to see things that you wouldn't be able to see with your optical telescopes. What these other graphs show you, this one just shows you total intensity, so you get most of the hydrogen coming from the center of the galaxy. What this does is this again is a measure of the Doppler shift of the hydrogen. And so what we can see is blue would be signal that would be moving towards you, and red would be things that are moving away from you. So what we can see about this galaxy is that this galaxy is spinning. And again, you can take a mathematical model, you can model what the kind of emission from a galaxy would look like and how the motion of that galaxy would govern that emission. And so now we can start building up classifications of galaxy, whether they're elliptical, whether they spiral, and what the dynamics of those galaxies are. Something else that CAT-7 does when it looks for pulsars is the nature of the emission from, as it moves through our galaxy, means that different frequencies will travel at different speeds. So that short burst of radio energy gets split up into its Fourier components, for those of you who are comfortable with Fourier. For the rest of you, it just gets spread out in frequency, and different frequencies will arrive at different times. And so what we do is we measure this slope with a telescope like CAT-7, and then by fitting this slope, we get an idea of what that signal moved through. And so now we've gone one step further. We haven't just understood what is creating the signal at its origin. We've now been able to classify or characterize what that signal traveled through as it moved through the galaxy to arrive at us. And so again, we're using the radio signal not just to study the source, but also study how the signal propagates through the galaxy and what is between the source and us. Another kind of study that CAT-7 does is a study of transients. Not all radio emissions are constant and unvarying, and studying how those emissions vary with time. So here we have days on the x-axis and the strength of the signal. What these different colors are from different telescopes at different frequencies. So we've got Hartebeeshoek and CAT-7 measuring. The nice sanity check is that the emission changes happen at the same time on the different telescopes. That's good. There are some slight differences in when these things happen, and that again tells you something about what is creating this radio emission. And the nice thing about a telescope like CAT-7 is because it isn't a mainstream telescope that has been allocated to people to do science, it can just sit and look at portions of the sky waiting for things to change. And once we observe something to change, we can then do follow-up observations. And again, that tells us just a little bit more about the science that goes on. Meerkat, well, Meerkat isn't gathering data yet, but it's real. This is a cartoon of what the dishes would look like, and this is an actual physical picture taken up in the Karoo of the first Meerkat dish. So it is a relief to know that Meerkat is actually real, and that the first dish should be producing data, I hope, within the week. Otherwise, I'm going to start having less and less things to worry about as our engineers delay things a little bit more. SKA, I'm not going to talk too much about the timeline. What is located where? well, Jeff was saying Australia lost. They didn't lose totally. It's a split, and so we're sharing the kinds of technologies. The way the technology was split was pretty much on frequency. And so the kinds of observations that Australia are going to be doing are with antennas that will look, we imagine, something like that. And that's the lower end of the spectrum. So they'll be looking for signals like the paper system was looking for. High Doppler shifted signals, understanding how that portion of the spectrum works. Africa will get mostly these typical looking satellite dishes, big dish with a receiver in front of it. A new technology called dense aperture arrays is also scheduled for Africa. That'll only come in the phase 2 part of the timeline. And the reason is because the amount of data that these things generate and the kinds of technologies needed to build this kind of telescope just don't exist yet. And so we can do all the sums on the back of a postcard and figure out the kind of compute power that we would need and the kind of receiver density and so on that we'll be able to need. And we know what we need to build, we just don't have the technology yet to build it. And so it's shelved for 2020 and so on. But what we are going to build so long are these, and so we're going to get lots and lots of those meerkat-looking dishes. Where will these dishes be located in Africa? Well, again, that principle of trying to make these dishes as far apart from each other, you can see we've stretched all the way up to Kenya and Ghana, out into Madagascar and out into Mauritius as well, and spreading out through Africa. Let me just skip through all those countries. I don't need to give everybody a geography lesson because everybody knows where we are. The kinds of things that you're going to be doing with SKA, well, pulsars, those things that emit the radio waves, what's nice is, like I said, they can be used for studying what happens between the origin of the signal and when it arrives at the Earth. And something that can distort these radio waves are something known as gravity waves. Electromagnetic energy can be distorted by mass, by gravity, and by changes in mass. And so another way to confirm or to refute Einstein's theory of how gravity worked would be using pulsars. What's sometimes called origins, or are there little green men out there? We don't actually look for little green men yet. Maybe we will see them, maybe we won't. But what we do look for is we look for the building blocks that make up life. And it turns out that different molecules and different chemicals, again, have their own discrete signature. And it turns out that some of them have signatures in the portion of the radio band that we're going to be looking at. And so we can have a look to see whether those molecules exist. And these are the kinds of molecules that have been found in space already. We found lots of water, and we found a couple of alcohols as well. So we definitely know there's a party going on somewhere out there. Again, our understanding of the cosmic timeline. I've said how we can look at the Doppler shifted hydrogen to know where we are in the universe. And so different things, as you look at things that are older and older and older, so their hydrogen should be further and further and further and further Doppler shifted. One of the things we don't quite yet understand is somewhere between where this Big Bang happened and how the universe is evolving now, some kind of energy was inserted into the system. Because if we just do the balance, if we take all the matter that we've been able to observe and the way we've modeled it, and we follow everything back, then it turns out that there was something missing. There's a whole bunch of energy that we can't figure and we can't see yet. And again, we turn on that lovely astronomy imagination, and because we can't see that energy and we don't know what it is, we call it dark energy. Again, imaginative to no end. So that's what we're going to be hunting for. A little bit further along, looking at those galaxies, looking at how they spin. Again, if you just do the basic sums and you measure how much the galaxy is spinning, and you predict how much matter there should be inside that galaxy to cause it to spin the way that it does, we find that there's stuff missing. Again, enter imagination, stuff we can't see, dark matter. But again, hopefully with telescopes that are more powerful, they will allow us to see something else that will give us a hint of what this information is. What you must think of is what it must have been like for the astronomers in the time of Galileo when he first invented the telescope. He looked up to the heavens, and up until then, they had a pretty good idea of what they saw, and they did not know what they didn't see. But the telescope, a simple telescope that we take for granted now, gave them a whole new way of looking at how their universe worked. And that's what we're hoping as well, is that instruments like the SKA will give us a whole new way of looking at how the universe works, maybe filling in these things that we can't see yet, giving ideas and meaning to these dark bits and pieces. I'm going to end off then with this notion of the African VLBI network, and that's to try and fill in this gap that exists in the VLBI network. Because you can imagine if we had radio telescopes scattered through Africa, then yes, we wouldn't be adding any dishes further and further away from each other, but we'd be filling in a gap of where there are pixels missing. And so what some bright spark did, a colleague of ours, Mike Gaylord, looked at Africa, and he found all the places where big old telecoms dishes have been replaced by fiber optic cables. And these are all the places that he found. And so he started contacting people in those countries to say, are you still using those dishes or not? And it turns out that there are a number of these dishes in Africa that, because fiber optic cables have now been laid all around Africa, they don't use these big dishes anymore. And so we can now turn these big dishes into telescopes. And so that's exactly what's happening in Ghana, Madagascar, Zambia, and Kenya. Sites that have been located already, and in some places actual hardware has already been installed in those places, and they are very close to becoming actual active radio telescopes. In Ghana, which is where most of the activity has been happening, they're actually in the process of getting this dish that hasn't worked for about 10 years or so. So it's just been sitting there parked. It's got rusty. You know, it's something when you leave it outside and don't worry about. The gears stop working, the motors stop working. Little bits and pieces disappear. We don't know why they disappear, but they do. And so effectively, we've had to rebuild. We've got all this steel, but we have to be able to make it move and to put signals on it. A system that we have from Mozambique, well, Mozambique didn't have one of these big spare dishes lying around. However, Telkom had a whole bunch of these smaller dishes that they don't use anymore. And so we've been retrofitting it to turn it into a radio telescope for deployment in Mozambique. Something else that we've been able to build, something that may look very familiar. This is a typical standard DSTV receiver dish. And what's connected to it is a whole bunch of would otherwise be complicated electronics and mechanics and machinery for a DSTV dish. And what this system actually does is this system accurately mimics every kind of mechanical interface that would be needed to drive a radio telescope. And so what you can do is you can take this thing to a country where a person has never seen a radio telescope before, never worked on the engineering subsystems and mechanical and electrical control and so on, and let them work on this, drive it, design computer systems to gather data, to monitor it and so on, and they can get first hands-on experience of working with a real radio telescope without actually having to build a massive thing. And so it's a very useful training tool. And again, our naming scheme continues. It is the baby telescope. Further opportunities, well, you know, we have opportunities right from bricklayers, plumbers, artisans, through in-service training for people with technician level, diplomas, undergrads, postgrads, and all the way up to PhD. So there's a whole range of training and development opportunities that exist the whole way through the spectrum, not just in the cutting edge front end science of radio technology and radio astronomy. So we're trying to build this whole big environment that is going to inspire the next generation. And what we hope that'll do is that'll address this graph. And again, this I stole from my colleague Kevin. And basically it's a graph of the return on investment compared to when you invest in a person. So sadly, all of you that are here at Ames doing some kind of postgraduate work, sadly, you are going to have a very low return on the amount of money that we're spending on you. Sad, but true. Had we caught you when you were about 4 or 5 years old and spent exactly the same amount of money that we're spending on you now, there would have been a much greater return on investment. So what does that mean? It means that, no, it doesn't mean we should stop giving you guys opportunities, but it means when you guys go back home and you want to have an impact, stop thinking about going to your first year class and tutoring, people at varsity and going to your high schools and speaking to people at high schools. What you've got to be doing is you've got to be enthusing parents and teaching parents how to communicate science and technology effectively with their children. And if you can get people talking about science and technology right from that very young age, then it's going to have a much higher return. People who are seen to have done well, the norm of exceeding in science and technology, you tend to find that they were exposed to technology at a very young age. And so if you want to take this forward, go back to wherever you came from, go back home, and connect with young people and inspire young people to talk about science and technology. And so I hope you get a sense that the South African government and South Africa as a whole is doing quite a bit to stimulate science, technology, engineering, mathematics. And one of the questions that's often asked at a time like this, well, shouldn't that money be better spent somewhere else? And I always like throwing up this infograph. And basically that shows out of every rand that is spent by the South African government, how much of it gets spent on science and technology. And so every rand that gets spent by this government, only 1.5 cents gets spent on science and technology. And so you can see there's a massive amount of return that we're getting by just that tiny little bit of investment. And so I don't think we're stealing houses from anybody. I don't think we're stealing hospitals from anybody. We're only tapping into a very small portion of that big pot, but we're doing a fantastic amount with it. And I think you can agree, this very first statement that I started off with, it's in the country's interest to facilitate modernization of African infrastructure studies and so on. I think we're on our way. We're not getting it 100% right yet. I think you'll all agree if you go back home, there are lots of your colleagues and so on who would wish for greater opportunities for African students. But it's not that there isn't anything. And hopefully you can take this message back and say that radio technology is hopefully improving things in Africa. So I'm going to leave it there. So thank you very much for your attention. Those of you who didn't fall asleep. And I'll happily take any questions if anyone has any questions. Yes?
How come South America is not involved?
So the whole concept of the whole SKA idea was opened where, and many countries were allowed to bid to host the SKA, and Southern America was one of those people who bidded to host the SKA. The trick is you want to be as far away from people as possible, which typically isn't a difficult thing to do in South America. The other thing is that you're building effectively a world-class data center in the middle of nowhere. So you have to be able to provision power and all the other services that are needed. And I'm only speculating here, but I imagine the cost and the technical difficulties in trying to move power and data to very remote locations in South America are more cost prohibitive than being able to do that in, say, Africa or Australia. But Southern America, and I think up in China and Russia and those areas over there where there's lots of open space as well, they were all considered for the problem too. But there are radio telescopes in South America. In fact, there's the world-class Elmer array, which is being built right up in the Chilean mountains. In fact, they're not linked to this. They operate at different frequencies. Again, another issue of just looking at things at slightly different frequencies. Yes?
Chile has radio astronomy, but maybe they aren't included because they weren't needed because they're looking into the same aperture in the sky.
It could be that. The point is that when you build up these images with your digital camera, the more pixels you have, the better your sensitivity is going to be. So there's never an excuse that, oh, we've got enough sensitivity. So you always want more. And again, it comes down to cost at the end of the day. If we had an infinite bucket of money, we would build a grid of these dishes and have them nicely spaced out. And because we don't, we have to optimize, and that means throwing out some dishes and so on. And it's not something we always want to do. The more dishes you have, the better. But I think it's just purely cost prohibitive to try and build the kind of array that SKA envisaged in South America, especially in the Chilean mountains. I mean, the mountain range is very narrow and long, which means the kind of way that you can spread the dishes out is very, very limited. But I don't think you'll ever hear a radio astronomer say, no, I've got enough dishes, thank you very much. I don't need any more. Yes?
Okay, as I understood, you got your money from South Africa, right?
Mm.
And I really wanted to know what is the implication of other telescopes spread out around the world with respect to your own.
Right. So the issue is that what is currently funded, and this is guaranteed funding, is the Meerkat telescope and the kinds of projects that I've outlined, the CBAS, the paper, the AVN, and so on. These are funds that are being contributed to by the South African government. The SKA Phase 1, what has been committed to is the design specifications for that telescope. So some stage between now and 2016, when they start building it, the international consortia that make up the SKA have to actually commit their funds to it. And currently, there are no other African partners within that consortium. And it's just the nature of the thing that I think they're waiting again for technology to evolve before they go to the SKA Phase 2 and then move everything up further north into Africa.
So it's really important to have the network.
That's right.
I mean, have more telescope around you.
Exactly, and the idea of the African VL network, taking those systems elsewhere in Africa and building related technologies there, is to create the skill base, the exposure, the understanding within those host countries, so that when the mainstream telescope needs to be deployed there, that you have a pool of people who know and who can talk the right kind of language and have the right kind of expertise for those. So that's why the investment is being made now, even though the deployment will maybe only be in a good couple of years' time.
Now, regarding the applicabilities, I mean, as far as understood, this is important for probing, for instance, the population of a country. That's the picture you show us. In the South Africa picture where you show the population, the red weight is what more dense and so on and so forth. And yeah, I'm wondering how.
Well, what is the application?
How do you measure this? I mean,
all of those bits of information are ancillary information. So that's information that has been provided by somebody else. We don't actually measure that with the radio telescope. What is of importance is the kind of technology that you use to build a radio telescope receiver is exactly the same kind of technology that a satellite company would use to build a satellite receiver. The same kind of technology and problems that you face in moving the massive amounts of data through our networks and so on are exactly the same kind of problems that the Googles and the IBMs deal with when they deal with their systems. So there are a lot of parallels in terms of technologies and training that if you use an incubator like radio astronomy, you can create skills that will very easily move across to other disciplines. And so that means that you could have a technician trained on a radio telescope that might very comfortably move into an industry application with just a slight change in terminology. Cool. Over there?
These satellites, you just mentioned the word satellite, are they a real worry?
Yes.
From the point of view of experience?
They are very much a concern. And there are certain portions of the electromagnetic spectrum that are reserved only for radio astronomy. And so basically what that means is that if we detect any emissions within that portion of the electromagnetic spectrum, we can find out, and we can find out who made those emissions. We have a case to the International Telecommunications Union to have some kind of sanction on those people. So that's the first thing. Places where the band is shared, we have to do our best to try and mitigate those emissions. So luckily enough, we have two things in our favor. Number one, either the satellite is moving really quickly relative to the sky, or if it's a stationary satellite, the sky is moving relative to the satellite. And so for a lot of our kinds of observations, the satellite isn't always in the wrong place at the wrong time. But yes, it is a problem. And I mean, let me give you an idea of the kinds of issues that we have. Satellite transmitters are very powerful transmitters, those sitting on the satellite, because that signal path has to get all the way from the satellite back down to your very small handheld device. So if you would think of the kind of emissions that you get from your cell phone. Now, a cell phone is typically a half a watt transmitter. If you took a cell phone and took it all the way to the moon and put it on the moon, it would be about 1,000 times stronger than most of the natural emissions that we're trying to look at with our radio telescope. And so man-made radio emissions are a big problem. And what you might consider in a normal environment, in an industry environment, is a very weak signal. For a radio astronomer, it's a very strong signal. So it's a problem that we have to deal with. Great.
So how do you detect the double shifted? I mean, it seems to be very important.
It's simple. It's simply that. So, for example, that galaxy that I showed, you point the dish at that galaxy and you measure the frequency of the signal that you're getting, and you see the amount that frequency emission is shifted from the 1.4 gigahertz. And
then you can claim that there is a reionization process.
So that's for a simple galaxy. For the reionization, it becomes a lot more of a statistical detection rather than a direct detection. Great. Well, thank you very much for your attention. Nice way to spend a Monday evening.